All right, so the next reaction we're going to do is an offshoot of radical halogenation. This is called allylic bromination. And before we get going, I'm going to show you a starting molecule. Looks like this. And like I said with radical halogenation, before I do any of my arrow pushing, I want to identify the hydrogen that's most likely to be abstracted. So for example, we've got this blue hydrogen over here. We've got this, let's say, green one right here. And then we've got a red one over here. I'll let you think about this for a second, but ask yourself which of these three hydrogens is most likely to be abstracted. And you can talk about it with your neighbor. All right, let's see a show of thumbs. Thumbs up if you think you've got it. Sideways thumbs if you're like, eh, and thumbs down if you have no idea what's going on. All right, looks like we're kind of all over the place, but that's okay. Let's take a look at the intermediate or potential intermediates. So for example, if we pluck off that red proton, we could have a radical right there. Do we agree on that? I think so. And then the second one, if we pluck off the green hydrogen, we would have a radical on that top carbon. And then same thing with the blue one. We could have a radical like that. So if we look at the top one, is there any resonance we can do there? No. What about the second one? Yeah, so let's try to predict what the resonance structure would look like for this second radical, and then check with your neighbor to make sure that you're doing the appropriate arrow pushing. Who thinks they got the second resonance structure? A few people? All right, so let's check the resonance arrow pushing. So for example, in this middle intermediate, we could delocalize this radical electron to the next door neighbor. However, it can't form a pi bond by itself. It needs a second electron. So it's going to steal one electron from the adjacent pi bond. However, that pi bond had two electrons, so the leftover electron has to go somewhere. So we'll dump it right there. So to show resonance for this intermediate, we need to include three resonance pushing arrows. However, make sure that they're only single-headed arrows, not double-headed. And that means, in the end, the pi bond would be right here, and our radical would be right there. All right, looking at the lower intermediate, meaning this one right here, does that have any resonance? No. So immediately looking at this, we could say the most likely hydrogen that will be abstracted will be this green one, because it results in the most stable organic radical intermediate. All right, so that's pretty easy to do. However, sometimes people forget to show all of the appropriate electron pushing arrows. So make sure you slow down and remember to include all of the necessary arrows, and don't get tricked into showing a double-headed arrow. Yep.
So when there's a positive charge, you can do hydride shifts. Is there anything like that with radicals?
That's a great question. So we saw with carbocations that they can undergo rearrangements. You don't see that with radicals. Yeah, great question. All right. So now let's take a look at what will happen here. So let's take the same example, starting material. I'm going to scroll this down. We had cyclohexene, and we said that this hydrogen coming off the top position is likely going to be the most reactive. And so we could say, well, if we react this with elemental bromine and UV light, one would predict that this hydrogen on the top would be abstracted and do the same sort of chemistry that we saw yesterday, right? So we'll draw this in here, and we could say, well, it's likely to go either from the top face or the bottom face. So a lot of times students will look at this and say, this is what I predict that we will get. The problem is this is not observed. Does anybody know another reaction that could occur rather than the radical reaction? Give you a hint. Got elemental bromine, got a pi bond. We could do addition. So instead of observing the radical product for this reaction, instead what is observed is anti-addition of bromines across that pi bond. along with an enantiomer. This is observed. All right, so then the question is, well, why aren't we observing any of the radical addition product? Why are we observing the regular pi addition product? This kind of gets into the nitty-gritty details. So the problem with this is that addition of the pi bond with the bromine outcompetes the radical reaction. So anti-addition of Br2 outcompetes the radical addition. So this was a problem that chemists tried to solve. They were trying to figure out a way of creating bromine radicals without having elemental bromine around. So how can we create a bromine with a single electron without having elemental bromine? So they had to go back to the drawing board and devise a new reagent. So I'll show you what the new reagent is. All right, and the alternate source of most bromine radicals comes from this weird ring system where we have a nitrogen that is covalently bonded to a bromine atom. This is called N-bromo succinimide. Most people don't call it N-bromo succinimide because that's a mouthful. Instead, they abbreviate it as NBS as a reagent. All right, so in the next step with NBS, we need to generate our bromine radical, and we can do that just like we did previously using UV light as our energy source. One electron in this covalent bond will get dumped onto bromine. The other one will go towards the ring side. So we get homolytic cleavage, which generates our bromine radical. The nice thing with this approach is we've generated bromine radical, but we don't have bromine in solution. All right, if you notice in my note, though, I said this generates the bromine radical without having a lot of Br2 in solution, but I didn't say no Br2 in solution. Why do you think that is?
Just a question about,
Yeah.
that's 4 carbons in a nitrogen, right?
Yes, 4 carbons and a nitrogen. So we've got a carbon here, carbon here, carbon here, carbon here, and then the nitrogen's kind of the other bridge. Yep. So you were talking about termination? Yeah, so if we generate this bromine radical, there's some statistical probability that this bromine radical will find another bromine radical, couple together and create some elemental bromine in solution. And so it's not that we're eliminating bromine altogether, it's that we're minimizing it, right? Because like I was saying before, when we do this cleavage, we're not generating a ton of bromine radical, maybe a percentage or two. And so statistically, we won't have a ton of bromine in solution, and we won't have a ton of the bromine radical in solution. We're kind of limiting both in this case. Does that make sense? All right, so now let's take a look at this mechanism. All right, so first part of the mechanism is just kind of a repeat of what we were looking at, where we have NBS in solution. We treat NBS with a UV light source, do homolytic cleavage, and we generate some of our radical. So now this nitrogen has an unpaired electron, and our bromine has an unpaired electron. Step 2 is just like what we saw before, where you have to account for your organic starting material and then your generated radical. However, like we said, we don't have a lot of Br2 in solution, so this time it won't do addition across a pi bond. Instead, it'll find that hydrogen that is most reactive. So it'll abstract the most reactive hydrogen and give you an organic radical. And we know that this is the most likely radical that will be formed because it's resonance stabilized. And now that we've done that, we can use the trace amount of bromine that's in solution. Like I said, there's not going to be a whole heck of a lot in solution, but these organic radicals are so reactive that they will seek out elemental bromine. It'll do a hydrogen abstraction, or sorry, a halogen abstraction, just like we saw before. This bromine can be installed on the top face or the bottom face. We know that we're going through a trigonal planar intermediate, so we would get these two products and we would regenerate our bromine radical. All right, let's scroll down a bit more. Our last step is termination. That means we need to eliminate our radicals in some way, shape, or form. Like we've seen before, one easy way of doing this is just to take both of your organic radicals, couple them together, and create elemental bromine again. So if we zoom out and look at this, students get really hung up on this, and they say, well, if there's bromine around, do we still get the addition reaction even a little bit? And the answer is yes. However, by limiting the amount of elemental bromine in solution, you can encourage the radical reaction to occur, so you won't eliminate the radical reaction pathway from this over-competition with bromine. Does that make sense? All right, so now I've got a harder one for you. All right, so for this one, I want you to provide the full mechanism using NBS and UV light, and then help me predict what product or products we would get out from this reaction. I'm going to include some hydrogens here just for our help later. So just like before, the first thing I always do is I look at all of the hydrogens on the molecule and I ask myself, which one's most likely to be abstracted? Blue? Okay, so you think blue is? I agree with that. If we were to abstract the blue one, not only is it coming off of the more substituted carbon, but what else is going on? Resonance, yes. So keep that in mind. I think too many students go through this and they just immediately jump to substitution without looking at resonance. Sometimes resonance occurs at a position that's not the most highly substituted. It just happens to be the most highly substituted for this one. anybody think they got this one? A few people? Who needs more time on this? All right, so I'm guessing most people are either stuck or need more time. So let's go through the mechanism. First step, like we saw before, is always going to be our initiation using NBS. We're going to use UV light. I'm going to scroll down here. And like we saw before, we're going to do homolytic cleavage to generate our bromine radical. And then step 2, we have our propagation. And just like we saw before, we need to identify the most reactive hydrogen, which we indicated was the hydrogen coming off, right off that central carbon. That will react with our bromine radical, and the bromine radical will steal it. So we'll do a hydrogen abstraction. The other electron from that covalent bond is going to be dumped down into the middle. So now we've got that tertiary radical that also has resonance. So let's draw the resonance structure for it. All right, if that radical moves, it's more likely to move over here. However, it needs 2 electrons to form a pi bond, so it's going to steal the second electron from the adjacent pi bond. And that means the leftover electron from that pi bond will get dumped onto that terminal carbon. So our other resonance structure will have a radical off to the far left, and our pi bond will be kind of in the middle there. So this is our resonance stabilized intermediate. We have also generated HBr, so we can't forget about that. And then in the next step, we're going to react this with elemental bromine. We said we would have a trace amount in solution. All right, so the question is, which radical is going to react with the elemental bromine, or can both? I would say they both can, right? That unpaired electron is residing on 2 different carbons. So for example, we could have this central carbon act as a radical and kick off bromine. And we would end up with the mixture of enantiomers, right? Because that bromine could add from the top face or the bottom face. And then we would also generate, or I should say regenerate, our bromine radical. Or we could have it react off of the other carbon, and we could say, well, this radical could grab the bromine as well. And just like before, we would regenerate our bromine radical. So if we think about the major organic products that we would get from this, we would get this one that I've boxed, or I should say 2, and then the one on the right that I've boxed as well. So it's probable that you'll get either of those 2 products. And then in your last step, just like we saw before, you could take 2 unreacted radicals and have them react together and do a coupling to form something like elemental bromine. Does that make sense? It's also, actually, I think I'm going to leave it at that. So the big thing to remember is the second step to account for the various resonance structures that you have, because your radical may be delocalized across more than one atom. Yep. Yeah. So at the end, we're just doing a termination step. So these are pretty useful reactions. Like I said, you have to be very careful to use NBS as your reagent. If you have any alkenes in there, you can't do elemental bromine, otherwise you get the competing addition reaction. Yeah?
For the 2 right before the termination step, is it like an equal mix?
Of the resonance structures?
Or of the product?
Yeah, that's a good question. I'm actually not sure if we would get an equal mixture or not. I know when we covered resonance structures, we said that there's major and minor contributors. In this case, they have full octets, both sides. And then you could argue about substitution and hyperconjugation. I'm honestly just not that sure. Yeah.
This whole reaction be done in the same flask?
Yes, so you'd have a hard time exclusively getting, let's say, this product over that product. Instead, you would just get a reaction mixture out of one reaction flask of all of these products. Does that make sense?
Are there side reactions that can take place with your initial radical organic radical, the one that's like the MPS or?
So your radicals can do other non-selective chemistry as well. However, these will be your main products that you would get out. Yeah.
So would this keep continuing for all of like the other side of the carbon as well? Because
That's a good question. So if we have excess NBS, we could potentially do another bromination. So for example, let's think about this compound right here. We could say, well, where's the next most reactive hydrogen on this compound? So for example, we could say, well, these two hydrogens right there, if we were to abstract either of them, we would again have a resonance stabilized organic intermediate. In order to do that, though, we'd have to have an excess amount of N-bromosuccinimide. Normally, people stop after just one addition of bromine. Yeah, I don't know if I've ever seen somebody purposely over halogenate. Good question, though. All right, so that's one of our two reactions from this chapter. The last one is one we've actually seen before, but we skipped the mechanism. And this is radical addition of HBr. So we saw this, I think, during our first or second day in lecture. All right. With this one, you can take an alkene, and if you react this alkene with HBr, well, you get Markovnikov or anti-Markovnikov addition. Markovnikov, right? So this would be your product. And like we said, this would favor Markovnikov addition. And then if we want to favor anti-Markovnikov addition, we still use HBr, but what was the other reagent? ROR. It's normally not done with hydrogen peroxide. It's normally done with alkyl peroxides. So those R's are indicative of some sort of carbon group. And when we do this, we're going to favor addition of the bromine to the less substituted carbon. So this would be anti-Markovnikov. All right, so this is the reaction we're going to focus on. When we covered it in chapter 9, we really didn't go over the mechanism at all. Yeah. All right, so let's do the mechanism. And the first step, just like with any of these, is our initiation step. So in this case, the weakest bond in our system is in the peroxide. So that oxygen-oxygen bond is incredibly weak. So it's pretty easy to cleave. You can pop one electron over to each side, and in fact, you don't even need UV light for this to occur. You just need heat. So we can show that with our delta symbol. So we generate two oxygen radicals in this process, and these oxygen radicals are highly reactive. And then step 2, we need to do our propagation with that organic radical. Actually, sorry, I'm going too fast. So we've generated our radical, but we haven't generated our bromine radical. So in the next step, we will have hydrobromic acid around. And we'll use this hydrobromic acid to generate our bromine radical. So in this case, one of these oxygen radicals will do a hydrogen abstraction. And then bromine will be kicked off as its own radical. So we will have made an alcohol from our oxygen radical. And then we've generated our bromine radical. Okay, so then the question is, well, why are we doing this fancy technique? Why don't we just use elemental bromine and do the normal halogenation? So peroxides are cheaper. They are easier to handle, but what would happen if we had elemental bromine? It would add across the double bond, so that wouldn't work. Why not use NBS then? So NBS, if we think about it, would do that allylic bromination that we just saw and leave the pi bond. We don't want to leave the pi bond anymore, right? We want to completely get rid of that pi bond. So in this case, an organic radical is another mechanism that peroxide radical is another mechanism we can use to generate a bromine radical. All right, and then step 2, we need our propagation. The propagation for this one is a bit different. We're not going to do a hydrogen abstraction. Actually, let me redraw this. So we've got our bromine radical right here. Instead of doing a hydrogen abstraction, what we're going to do is addition to a pi bond. So this is going to try to form a new covalent bond with that carbon that's next to it. However, in order to do so, it needs a second electron. It's going to steal that from the pi bond. And then the other electron from the pi bond is going to get dumped into that central carbon. So this explains the regiochemistry a lot more, right? So if we think about the bromine when it's adding in, it prefers to go after the more accessible carbon due to sterics. So it's easier to react with one of the exterior carbons than that interior carbon. And then second of all, this intermediate has the radical unpaired electron on the more substituted carbon. So it's much more stable than having it on a primary carbon. All right, and then in the next step, we're going to have this react with more HBr in solution. And this radical will steal a hydrogen from HBr and then kick off an electron onto bromine. So now we'll have a hydrogen there. And we've regenerated our bromine radical, which is important for that propagation step. All right, and then the last step is termination. And with termination, like we've seen before, you can take any remaining organic radicals and have these coupled together in order to form your elemental bromine. So the key difference, in this reaction is this step right here. So in this step, we do addition to pi bond. Not hydrogen abstraction. So it is slightly different than what we've seen in our previous examples. Does that make sense? Yeah.
What exactly did tip them off about Rachel with the anti-Markovnikov about it in the peroxide? Like, what did they detect, the alcohol?
Yeah, that's a good question. So the question was, how did they know that peroxides played a role in the anti-Markovnikov addition? They didn't know the full mechanism at first. What they did know was that purity mattered a lot. So what some chemists did was they were meticulous with their reactions. They would maybe get bromine and they would say, I don't trust this bromine. Maybe it's got an impurity in it. In fact, I'm going to purify it myself. And then they would test it. And then they found that if I purify that bromine and I'm confident it's 100% pure, it favors Markovnikov addition. Or I should say HBr, sorry. However, they noticed that some impurities like peroxides do the opposite. And so they were trying to figure out what the impurity was that mattered, and they settled on peroxides. It wasn't until, I'm assuming a little later, that they were able to understand the full reaction mechanism. Yeah, these reactions were discovered, honestly, before we had a solid understanding of organic chemistry as a field. They were kind of just guessing at a certain point to figure out what was going on. Yeah. All right, we've got, I think, about 10 minutes left. I think that's where we're going to stop today. I'll give you these last 10 minutes to start on your problem of the day because it is a little bit more challenging. So try to see if you can work backwards from your pod. So look at your final product and ask yourself, what intermediate do I need to make that final product?